Hello everyone, I'm Agneet, and today I'll be talking about our work, Getting It Right, Improving Spatial Consistency in Text-to-Image Models, which will be presented at ECCV 2024. This work is a joint collaboration between Arizona State University, Intel Labs, Hugging Face, University of Washington, and University of Maryland, Baltimore County. One of the major struggles of text-to-image models is their inability to generate images that faithfully respect the spatial relationships mentioned in the input prompt. As shown here, the models either fail to generate both the objects mentioned in the input prompt or are not able to generate images where the spatial relationship is mentioned. In this work, we aim to solve this problem. Specifically, we develop datasets, methods, and present insights that enable a deeper understanding of spatial relationships in text-to-image models. Our first finding is that existing visual language datasets underrepresent spatial words. Specifically, words such as left, right, above, below are scarcely present in current datasets, despite being widely used in the English vocabulary. Shown in red are examples from existing captions. In green are captions from a sprite dataset. We leverage state-of-the-art VLM Lava to recaption images across 4 datasets: Coco, CC12M, Lion, and Segment Anything. We find that Sprite largely improves upon the ability to capture spatial phrases and the relationships mentioned in the images. Further, we perform a threefold validation to study the correctness of our captions. We use GPT-4V, human evaluations, and question decomposition methods such as Fate Score to evaluate our generated captions. Once Sprite is created, we follow the experimental setup as shown below. Our base model is Stable Diffusion 2.1. We train on 13,500 images and validate on 1,500 images from Sprite. We train on a ratio of 50% spatial and normal captions, and we fine-tune both the UNAT and the clip with a learning rate of 5e to the power 6. We find that using only 15,000 images leads to a large gain in generating spatially accurate images while also improving image fidelity metrics such as FID and CMMD. Next, we also devise a training technique which turns out to be more effective and efficient. From our 13,500 images, we bucket our images depending on the number of objects they contain. We use Recognize Anything, an image tagger model that generates a number of unique objects in an image. We find, as shown below, that despite having a small number of images, using images with multiple objects leads to a significant gain in spatial score. Shown here are scores of FID, CMMD, and Visor. We also lead to large gains in performance across all aspects of the Visor metric, specifically on the Visor 4 score, which indicates that our method can consistently generate spatially accurate images. Shown here are results on GenEval, where we improve performance across tasks of counting, colors, and multi-object generation. Despite not explicitly optimizing for it, we also improve performance over baseline methods on aspects of compositionality such as color, shape, and texture, as is shown on the T2I component scores. Here are some qualitative results that are from the T2I comp bench dataset. Further, we compare FID scores on Coco, baseline, and our fine-tuned method and see that our method is more prompt following. We find that a ratio of 50% and 75% of spatial captions is optimal, while all spatial captions lead to catastrophic forgetting. Long captions lead to better performance across multiple settings, as evidenced here. We also perform analysis on our fine-tuned text encoder to understand the impact of fine-tuning it with spatially focused captions. Shown here are results on centered kernel analysis, which shows how different layers of the baseline and fine-tuned clip behave differently to spatial captions. MLP and attention projection layers are more conducive to learning the spatial nuances, whereas layer norm layers do not have a large change in the learning patterns. Inspired from methods such as Attend and Excite, we find that Sprite leads to better localization of attention maps across the final image and the subwords, including spatial relationships. Finally, there is scope of improvement. For example, the quality of captions can be improved while using larger models. We also do not perform scaling studies, which is left as future work. Furthermore, there has been a recent surge of different architectures such as diffusion transformers and autoregression generation of images. The impact of Sprite can be studied there. Thank you for your time. This link will lead to the project page. Hope to see you soon. Thank you.